All right, welcome back to the second video for the periodic trends topic. Last time we spent the whole day talking about Coulomb's law, right, which is that mathematical formula that you can use to describe or understand the behavior of charged particles. So today we're going to be using Coulomb's law to kind of explain how periodic trends work. Okay, and the two periodic trends that we're going to look at are the atomic radius of elements and the ionization energy of elements. So we'll go through and talk about what these mean, we'll talk about what periodic trends are, and we'll talk about what the periodic trends are for these two different properties. Okay, so moving right along here, what are periodic trends? Okay, so periodic trends are general rules concerning properties of elements on the periodic table. Okay, periodic trends can be either period trends or group trends. A period trend is how a property changes as you go across a period or across a row on the periodic table. So as you go, say, from left to right across a row on the periodic table, how does a certain property change as you go from left to right? A group trend is sort of the opposite of that, right? How does a property change as you go down the periodic table? So not across, but down a group, say from top to bottom. How does a property change as you go from top to bottom? Several periodic trends can be discovered on the periodic table, but we're going to focus on two for this class. Okay, we're going to focus on atomic radius and ionization energy. Okay, so we're also going to be using this diagram here, which I included in the follow-up video after our lesson on the electron configuration in the periodic table. These are Bohr models of some of the first few elements on the periodic table. Okay, and in fact, this goes through the fourth row from groups 1 to 18, technically. If you watched that short little 8-minute video, if you haven't watched that video, I would go watch that really quickly. But if you have, you'll remember that if we skip the transition metals in the center portion of the periodic table, the D block of transition metals, then what we have here are the rest of the elements here. And I talk about valence electrons and things like that in the follow-up video. So once again, if you haven't watched that short 8-minute video from 2 class periods ago, make sure you go watch that. But anyways, we're going to be using these drawings here, these Bohr models, to sort of help us as we go through the lesson today. Okay, so first thing that we got to talk about is what is atomic radius? Okay, well, atomic radius, or radii in the plural, of an atom is the measure of that atom's size, right? It's basically how big is the atom. I guess technically atomic diameter would be truly like the size, but knowing the radius is essentially the same thing, right? Because 2 radii is equal to the diameter. So despite being very small, okay, atoms are very, very small, scientists can actually experimentally determine the radii of atoms by measuring the distance between nuclei in chemical compounds. So whether you're talking about a metal or some sort of covalent compound or an ionic compound, which we're going to learn about later this year, you can measure the distance between 2 atoms, split that in half, and then you're left with the radius, right? That's not really super important for us at this moment. What we are going to talk about is the atomic radius trend, okay? And actually, let me go back to this image here. We're going to talk about the atomic radius trend. So how do atoms change in size as you go across a row? And then how do atoms' sizes change as you go from top to bottom, okay? Now, the group trend, we're going to get to this in just a minute, but I'll spoil it for you here. The group trend for atomic radius is super easy, right? Think to yourself, how do the size of atoms change as you go from top to bottom? Do they get larger or do they get smaller? They obviously get larger, right? You can see here clearly, just with this little model here, these Bohr models, it's very clear that atoms are going to increase in size as you go down a column, okay? What is less easy to explain, and in fact is a little bit counterintuitive, is the period trend. How do the size of atoms change as you go across a row? I'm not going to spoil the answer on that yet. The first thing we need to talk about in order to understand why that trend is the way that it is this concept of nuclear charge, okay? So nuclear charge is the amount of charge in the nucleus. Okay, duh. We're going to use this variable z to represent the nuclear charge in an atom. Basically, guys, it's just the number of protons. Okay, so if we look at this nucleus, keep in mind that a nucleus has protons and neutrons. I can't tell which are which here. It looks like there's seven different particles in there. So maybe there's 3 protons and 4 neutrons. I don't know. The nuclear charge of an atom or of a nucleus is just the number of protons that are present. Okay. So here's a really easy trend for you. Okay. As you go from left to right across a row on the periodic table, the nuclear charge of elements increases, right? The atomic number is increasing, right? So if I go back here, lithium would have an atomic, lithium has the atomic number 3, so its nuclear charge would be 3. There's 3 protons in this nucleus. Beryllium would be 4, boron is 5, carbon is 6, all the way down to number 10 with neon, okay? So nuclear charge increases as you go from left to right across a row on the periodic table, okay? So why does that matter to us? Well, we want to know, right, how would the atomic radii of atoms change as you go across a period or across a row on the periodic table? Let's try to think of it in terms of the nuclear charge, okay? As you go from left to right across a period, what happens to the nuclear charge? It goes up, right? So we have more and more positive charge inside of the nucleus, okay? And be thinking about Coulomb's law, right? So we've got a greater amount of charge in the nucleus. How would that affect the electrons that surround that nucleus? Okay, think about that. And sometimes it helps if you look at this picture here, right? So these black circles at the center of each atom, that's our nucleus. And this nucleus here only has 3 protons, whereas this nucleus over here has 10 protons. I realize that there are more electrons, right? But they're all in the same energy level, okay? So as you go across a row on the periodic table, the nuclear charge is increasing, but the energy level is staying the same. So the question is, right, what is the trend? Do the atoms get bigger or do they get smaller, right? Well, the answer is, okay, that atomic radii actually decrease as you go from left to right. Atoms get smaller as you go from left to right across a row. The nuclear charge increases as you go from left to right, okay? And so as you move from left to right, the electrons surrounding that atom feel a stronger and stronger force of attraction from the nucleus because that number of protons is going up, right? And so therefore, the electrons are sort of more tightly bound and sort of shrink in closer to the nucleus. So the atomic radii of atoms actually decreases as you go from left to right across a period on the periodic table. And like I mentioned before, this has been experimentally determined to be true when chemists and scientists analyze the size of atoms in real chemical compounds. Okay, and we also talked about the sort of no-brainer, right? Atomic radii definitely increases as you go from top to bottom down a group, right? And this is because atoms are simply just growing in size due to an entire additional energy level of orbitals full of electrons, right? So the atoms are literally just getting bigger because we have more and more energy levels full of electrons. Okay, so that's the period and group trend for atomic radius, all right? Next thing I want to talk about is ionization energy, okay? And this is a little bit tougher because, you know, atomic radius, that's a little bit, you know, intuitive, right? It's just the size. But you guys probably don't know what ionization energy is. So here's your definition for you. Ionization energy is the energy required to remove a single electron from a gaseous atom or ion. It's not super important that it's a gas, okay? But just think about the first part of that sentence there. The ionization energy for an element or for an atom is the amount of energy required to remove an electron from that atom, okay? And it can be expressed like this formula here. So we're taking an atom and converting it to a positively charged ion plus an electron. We are removing this negatively charged electron from the atom, and so that results in the atom having an overall positive charge. We're going to talk a lot more about ions later in the year, but basically we're just removing an electron from this atom, okay? So let's think about this, right? How would ionization energy change as you go across a period and down a group? Well, in order to really understand this, there's a few other concepts that we need to bring up, okay? The first one is something that I hope that you know about. If you watched my 8-minute follow-up video, you should recognize this term. Just in case you didn't, or if you haven't watched that video yet, I'm going to go over this again right here. There are two different types of electrons in any given atom, okay? There are valence electrons, which are the electrons in the outermost energy level of an atom, and there are core electrons, which are the inner electrons, okay? So if I look at this Bohr model here, the valence electrons are the 5 electrons here in the second energy level, the second ring. Those are the 5 valence electrons. The core electrons are these 2 in the first energy level, okay? And if this were a much bigger Bohr model, then I would have a lot more core electrons, okay? Your valence electrons are only ever going to be the very outermost ring, okay? And in fact, you can never have more than 8 valence electrons due to how electron configurations work. Okay, so we've got valence versus core electrons. So the presence of core electrons can do something kind of interesting, okay? So we've got positive charge in the nucleus, right? Here's that letter Z again, representing the nuclear charge. So the positive charge in the nucleus attracts electrons, but core electrons can repel other electrons. So let's pretend that you're this guy, okay? You are this electron here, a valence electron. Let's talk about the types of electrostatic forces that you are experiencing, okay? You are negatively charged, and the nucleus is positively charged. So you are feeling a force of attraction towards the nucleus. That's represented with this light blue arrow. However, there are inner core electrons present here that are also negatively charged, okay? So they have the same type of charge that you do, and so they are actually going to repel you away, okay? So the presence of core electrons repels valence electrons away, okay? Now overall, the nuclear force is going to dominate, okay? So you are still being attracted to the nucleus. You're not going to fly off out into space, but the total amount of force that you feel is mitigated somewhat or lessened somewhat by these electron-electron repulsions. Okay, and that's actually what they're referred to. They're called electron-electron repulsions, and they cause the total force of attraction on the outer valence electrons to be lessened somewhat. Okay, this phenomenon is referred to as electron shielding. Okay, the core electrons, in effect, act as a shield, kind of like a negatively charged shield, that repel valence electrons away somewhat. Okay. I want you to be a little bit careful, okay? And this is a slide that I had for my AP Chemistry kids, okay? So you don't have to be quite a master of electron shielding as they are, but let's be careful about how we talk about it, right? The valence electrons do still feel the full attractive force of the nucleus. They still feel the full positive force. The overall force that they feel, though, is somewhat smaller due to the repulsive force of the core electrons, all right? So they feel the full positive force, but they also feel a repulsion or a repelling force, and so the overall force is smaller than the total positive force. It would be incorrect to say core electrons shield valence electrons from feeling the full attractive force of the nucleus. They do still feel the full attractive force, it's just that they also feel a repelling force, and so the sum of those two forces, sort of one positive, one negative, it balances out to be smaller than the original attractive force. Okay? All right, so let's talk about ionization energy then, okay? Well, ionization energy, the amount of energy you have to spend to take an electron away from an atom, that amount of energy increases as you go from left to right across a period, okay? And here's why. Okay, let's go to our drawing here again, or our Bohr models. This element here, lithium, has 3 protons, right? Neon has 10. Okay, so let's consider those two sort of end scenarios, right? So we have 3 protons here, 10 protons here. In both cases, lithium and neon have the same number of core electrons, right? There's only 2 core electrons here, and there's only 2 core electrons here. So the amount of electron-electron repulsions is sort of equal. You see what I'm saying? But what's different is the nuclear charge, right? Lithium has 3 protons, neon has 10. So to remove a valence electron from neon, it's going to be a lot tougher, right? Because these valence electrons feel a much stronger attractive force than this one valence electron on lithium. Okay? Hopefully that makes somewhat sense, right? As you go from left to right, the nuclear charge is increasing. Therefore, the valence electrons feel a stronger force of attraction towards the nucleus. Therefore, it's harder to pull them away. Okay, and that's what ionization energy is. It's the amount of energy or the amount of work you would have to spend to pull that electron away, completely remove it from the atom. Okay, so, oopsie, sorry about that. All right, so that explains the period trend. Okay, and ionization energy increases as you go from left to right. As you go from top to bottom down a group, there's a number of different factors at play. Okay. While the nuclear charge does increase, okay, so you do have more and more protons as you go down, you're also getting further and further from the nucleus. Okay, so remember that R squared term in Coulomb's law, right? As an electron gets further and further away from the nucleus, the amount of force that it feels goes down. Okay, plus, okay, additionally, there are a lot of more electron-electron repulsions that you have to worry about, right? As an atom gets larger and larger. If I go to my Bohr models here, let's compare lithium to sodium, right? So not only is sodium's valence electron further away from the nucleus, resulting in a lower attractive force, it also has all these extra core electrons that are repelling it away compared to lithium. And so both of those factors combined result in a decrease in the amount of energy that you have to spend to take the electron away. It becomes easier and easier to peel off the valence electrons as you go down a column for both of those reasons, right? You're getting the electrons are further from the nucleus, and there's more electron shielding coming into play, okay? So once again, ionization energy decreases as you go from top to bottom down a group, okay? All right, so that is basically the gist of what I need you guys to know. What we're going to do in class next time is we're going to work on an assignment, and you're going to be using the trends to sort of predict the properties of different elements. And you're also going to need to explain why the trends are the way they are. That's what I've tried to do in this video. Feel free to come back and watch the video as you're working on the assignment to help you in your explanations. But that's really important for me, is for you being able to explain in terms of Coulomb's law, nuclear charge, distance from the nucleus, electron shielding, those types of terms and those types of concepts. I want you to be able to explain why, for example, potassium would have a lower ionization energy than lithium. Or, for example, why oxygen atoms are smaller than carbon atoms. Okay? So you need to be able to use the different concepts that we've talked about in the video today to explain why those things are the way they are. Okay? All right, that does it for the video. I hope you guys enjoyed it. I will see you guys in class next week.